If you want 1,000 sampling, you take look at 1,000, and then you want the confidence level be 80%. That means you only look at 10% on the right, 10% on the left. You don't care. If you want this 80% of confidence, then you're going to find most likely. This is called most likely. It's between 73.2 to 76.7. That's the number. That's when do you remember? If the particles were polling, the typical polling of 1,000 people, and they tell you the error is plus minus 3%. The politicians, they keep doing that. That's a standard way. And that's exactly, you can see from 72, that's 2% plus and minus, right? And then this, if you put this minus this, you can see that's about 3.5% error. That's what they always claim to you. The error is about 3%, and they're putting 1,000. That's pretty much standard deviation. You can always remember that. And the next time you're going to see the claim, Jeb Bush will win by how much percent? 53%, but plus minus 4 points of error. That means nothing. It means it did not tell you anything. It just make you feel he's going to win. Okay, now if you do 100, look at that number. How much bigger? That's 10%, right, of the error between. But the middle is still 75. Now look at carefully. If I only do 10, what's going to do? If I only got 10, you got this. Could it be anywhere from 55 to 88%? Well, I just looked at the dictionary, figured out what that means. Should it be taken with a grain of salt? What that means? Google it. I just Googled it. It's interesting saying. Yeah. If you're not a native speaker, you need to take it out. Basically, don't take it too serious. That won't make anything really predictable. However, a lot of times we have to rely on this because that's all you have. What you say. That's when we don't use the normal distribution. Instead, we're going to use the so-called T distribution. It's called the student distribution. They're going to spread a little bigger and they give you less crackability. Okay, I have to be fast. Holdout estimate. The key for the holdout depends on the size of the data. What you really need to watch the data is they need to be diversified enough, covered all different kind of combination. For instance, that's the ideal case. But usually it's not possible. Even this is not possible, you need to pay attention to see if the testing set and the training set, they have a fairly good coverage, diversified coverage, similar coverage. If not, they either give you a very pessimistic result or over-optimistic result because it's not trustworthy. So that word, stratification, is a very, very important word. That means when you are sampling it, you're not just a complete random sample. You need some randomness. What they want to say. But you need to pay attention to those rare cases and to make sure it's covered. Unless you covered in the training, you are not going to test correctly in the testing. If you don't cover in the training, you do the testing, you're going to fail, right? Just like I don't teach you and then test you, and you don't know where it is. Another way is also true. And if you train in not testing, you don't get the benefit either of the optimistic. As another strategy, besides the stratification, is if you have the data, try to do a few rounds. In each round, you always take one part randomer, like 2/3 as the training and 1/3 as the testing. But you got another separate set to do the same thing each time. and then you're going to average. If you do this, you're going to improve the credibility of your training and the error rate. But this is still not good. Why still not good? Because this, you still have a possibility of overlapping. Most of the time, you don't have the luxury to get all completeness subsets to do that, because your data set is expensive. Regardless, even online data is expensive. You need the labor. And then you're going to reuse it. Just each time you do a little bit different sampling, 2/3 go training, 1/3 go testing. But no doubt, when you repeat it, you got a lot of overlap. This overlap gives you a little bit of false optimistic. Get it? So that's what we call overlapping. How can we handle that? If your data is fairly good enough, that's the most frequently used, called cross-validation. The cross-validation split the data into K subsets. That's called the K-fold cross-validation. This K most of the time is 10. Why? You're going to read the paper. Why is 10? You know, the weight by default is 10. Then you're going to split your data into 10 pieces, equal, randomly. And then each time you're going to make a 9 to do the training, and the 1 to do the testing. But the next time you're going to take another one of the 10, save as testing, get the rest of 9 to do the training. And then the third time you're going to go to find the third reserved one as testing, the other 9 to do the training. That's the most, one of the most frequently used approach to deal with lacking of data. I still want to do the average. And then you're going to do this 10 times. That's called 10. Another one is called the leave one out approach, like the weather example. I only have 14. What I'm going to do is each time I pick one out to put it aside, and the 13 to do the training, and then use the 1 for testing. That's a little issue. And that testing only fail or succeed, either 100% or 0%. But if you do 14 times, you're going to use the 14 times test result as average. And basically, you use the 14 times also by doing the testing, right? But average, the 14 times of success rate is a good deal. And that's called leave one out approach. But the computation, you're going to do how many times? 14 times 14 times of the computation. Because each time you did the 14, each time left 1 out, and then you do another 14, and that's the computation. 14 is no big deal. But if this is 140, 140 times 140, you have to do how many times? But leave 1 out, there's one problem. You can get 100% of error. That's what I said. Let's say you have a random probability for 2 classes. And you leave 1 out, this 1 out in the testing is either get all or nothing. And but sometimes you have no other choice. That's a good choice. Another, I think this is a very good approach, like the cross-validation approach. Bootstrap. Bootstrapping is very simple, and to me, this is also a good word doing the research, Google research. And the bootstrap means you're going to use all data. Each time, if I have 14, I'm going to select the 14. But with placement means I'm going to probably select the same 3 times. Typically, if you keep doing it, you're going to get 65% you selected because you repeat it, right? Another 30-some% will be leave out as testing. And then you do this many, many times, you average it. That's called a bootstrap. For small data. And Why 33%, 36%? That's just honest formula. Because of the repeating process, if you fail to be picked in the n times, it's a number. When n is too big, that's E. That's 1 over E. That's 37%. 37%, you're not going to be picked. If n is big enough, you repeat. Let's say I have 1,000. 1,000 the sample, you pick, you know, you're going to have a lot of repeating. But the most likely, 80% time, you're going to have 37% of never be picked. But this 368 sample, you put it aside as testing. When you finish this round, you put them all back again. And then you randomly pick again, another 632. And then you put the other leftover as a testing. You do this as many times, you average it. That's a good deal. That's a very, very nice way to deal with a small data set. But there's a problem for that. Because you always use the 32% never seen example to testing, you end up get a very pessimistic estimate of your error. Because everything you do the testing never seen in the training. And each time you do this same way, right? So because it's too pessimistic, you do the error in this way. You give most weight to the testing error. That gives 62%. Now, on the other hand, reverse it. Give the 65% of a training instance also credit of the error. And then in that way, then you're going to kind of lower down the average error because you are pessimistic approach. That's how you give a fair comparison.